Welcome everyone to the first session of the breakout sessions for the Carbon Positive Reset 1.5 degree global teach-in. We'd like to thank our partners for their support in developing today's content and supporting the event. Today we are in the session Design with Climate, Form Follows Performance, Energy Efficient Passive Design and Zero Carbon Buildings. If any of you are interested in continuing education credits, this is the description and learning objectives. Following the teach-in, we will have an email form sent to you for you to complete, and we will follow up with your continuing education providers with additional information for you obtaining credits. Also note that we will have a question and answer session at the end of this session. You can type in your questions in the Q&A box using the Zoom panel. If it comes into the chat window, I'll also collect them, but we'll be following the Q&A section. Any unanswered questions will be answered by writing and posted on the website after the teach-in. My name is Vincent Martinez. I'm the Chief Operating Officer for Architecture 2030. I'll be acting as moderator for today's session. I have the pleasure of introducing two esteemed colleagues as our panelists for today, doing co-presentations. One is Alfredo Fernandez-Gonzalez, who is a professor at the University of Las Vegas School of Architecture and a founding director of the Natural Energies Advanced Technologies, aka NEAT laboratory at the university. We also are joined by Pablo Roche, who is the Global Sustainable Design Leader at CallisonRTKL, and a professor of architecture and interim director of the Lyle Center for Regenerative Studies at Cal Poly Pomona University in California. He also has a new book out titled Carbon Neutral Architectural Design. Again, today we're talking, this is the session Design with Climate, Form Follows Performance, and I will let Alfredo kick us off.
Hello everyone, and thank you Vince for the introduction. In this session, Pablo and I will talk to you about climate-based design. And here we go. For architectural design purposes, a climate classification that addresses the challenges that we face to deliver thermal comfort is what is really needed. And as human thermal comfort depends on the dissipation of the body's metabolic heat, discomfort will occur when there is insufficient or too much heat dissipation. And as we are reminded by Jim Augustine in his wonderful book, The Return of the Solar Cat, buildings should recognize the influence of the climate and really take advantage of passive design strategies, which is the focus of this session. Since solutions need to emerge from place, in this session, we will use a climate classification that addresses the thermal issues associated with the provision of comfort. And for convenience, we have grouped the ANSI ASHRAE Standard 169 in 4 different categories: hot, humid, hot, dry, temperate, and cold climates. Here, using the bioclimatic chart as a reference, we can see the approximate range of conditions of our 4 climate zones, the ones that we've just defined. And if you're not familiar with the psychrometric chart, on the horizontal axis, you have dry bulb temperature. On the vertical axis, you have absolute humidity, and the curves that you see inside the psychrometric chart correspond to relative humidity information. So the temperature and humidity range of the temperate climate zone is generally associated with thermal comfort, and therefore the upper and lower limits of this temperate zone are really important from a design perspective. So the red line that just appeared corresponds to what we would call the shading line, and the shading line suggests the times when we need to begin implementing shading, both for our windows as well as outdoor spaces. So when the temperature rises above that red line, shading becomes necessary. The blue line corresponds to the upper limit of the temperate climate zone, And this constitutes the cooling line. When the temperatures rise above that cooling line, some form of cooling needs to be provided to achieve thermal comfort. So this again is initial reference. I want to plug in a fantastic resource which is developed by Professor Moray Milne at UCLA. This is a climate consultant, a program that allows you to very quickly conduct a climate analysis of really just about any location on Earth. And here you see appearing those two lines I had just mentioned before, the shading line and the cooling line on the psychrometric chart for the city of Las Vegas. And the box which you see on the upper left gives you the percentage of time in which conditions fall within a given passive strategy. So that's how we can make conditions comfortable. So let's talk about cold climates. And cold climates typically occur at latitudes that are higher than 40 degrees north or south from the equator, or at very high elevations greater than 7,000 feet or 2,100 meters above sea level. And in these kinds of conditions, a well-insulated building is a prerequisite. In addition, solar radiation, gain, and thermal mass are both needed to achieve thermal comfort. So let's talk about the form that buildings should pursue in cold climates. So we'll basically through some series of quick slides. A building elongated along the east and west axis provides the best performance for winter heating, but also for daylighting and summer sun shading. And as a general rule of thumb, a building width should be approximately 5 times the floor to ceiling height. So if windows are available on both sides, this allows for excellent daylighting distribution and ventilation during the summertime. The length of the building should be as long as reasonable. If a building gets too long, consider making it 2 or 3 stories higher or as tall as needed. In the Northern Hemisphere, during the winter time, a building elongated along the east-west axis will expose its roof and south facade to incoming solar radiation. Correctly placed fenestration along the roof or the south wall will allow for passive solar heating during the winter. And in the Southern Hemisphere, we would aim to expose the north-facing roof and facade to incoming solar radiation. During the summer, it's critical that we provide a properly sized overhang to provide the shading to the windows that were used for winter sun collection. Remember to keep the east and west facades, along with other certain roof areas, shaded as possible, so that, in spite of the fact that this will receive the largest amount of radiation, they need to be protected in the summer to avoid overheating of our building. I also want to plug in a very important resource, which is the Architecture 2030 Pallet. The 2030 Pallet provides you with tremendous resources to provide initial guidelines during the design process. And today I just want to show the example of sizing windows for direct gain. And when you click into this strategy, then you will see, among the many pieces of information there, you will see a very detailed guideline to size windows, to size glazing for passive solar heating. So continuing with the form for heating in cold climates, the form that is narrow, the floor plate that is narrow, it's also critical for successful natural ventilation when this is considered. This allows us to effectively ventilate the building, having windows on both sides. To enhance the performance of cross ventilation, one of the building's long facades should be oriented as close to perpendicular to the prevailing wind direction. The compromise between winter solar heating and natural ventilation may be obtained by rotating a building up to 30 degrees from the equator facing orientation. Heating and cooling requirements need to be considered before making the final decision. And in spaces with a floor plan, partitions should be oriented perpendicular to the windows for better daylighting penetration, as well as to maintain adequate airflow during ventilation mode. Now I'm going to show you a case study of a building which is net energy positive. In fact, this building produces more energy than it consumes on a yearly basis. The building is located in climate zone 7B, and it's located in Basalt, Colorado. Here are some relevant parameters about this particular building. And I want to emphasize the building form follows the east-west axis. Recommendation we just made has a very narrow floor plate, butterfly roof with higher ceiling near the windows to maximize daylight penetration. And it has obviously a highly insulated envelope following passive house standards and large south-facing windows to provide passive solar heating with active solar gain controls. So here you see the elongated plan along the east-west axis and a window to wall ratio of 52% on the south versus 18% on the north. So windows maximized for daylighting, ventilation, and passive solar heating. The narrow plan permits also the penetration and good distribution of daylighting. And that same narrow plan also allows for successful natural ventilation of the spaces during the summertime. The building maximizes passive solar design and is really insulated to meet passive house standards. Also to improve, as we mentioned, to improve both daylighting performance and passive solar heating, the building features a butterfly roof to have a higher ceiling near the windows, particularly the south-facing windows. And in addition, to minimize glare and to control solar heat gain, the building features automated exterior sunshades. This is a view of the south facade without the south-facing window sunshades deployed. And this is a view with the automated window sunshades deployed to control glare and solar gain. Thermal mass in this building is used to both absorb solar heat gain in the wintertime and to pre-cool the building at night during the summer for improved comfort during work hours. And here you see the smaller photographs on the right show the circulation area provided near the south-facing windows, which creates a thermal buffer zone. And through the addition of the lower bookshelves, you also see here, these bookshelves serve as partitions, but they also reduce glare on work surfaces when solar radiation is coming through the windows. By contrast, in the lobby area, where we don't perform visual tasks, we have solar radiation absorbed directly by the floor slab and very vibrant and open space where solar radiation contributes to the heating of it. And finally, natural ventilation during the nighttime allows the building to fully maximize its thermal mass throughout the day. Taking advantage of the cold evening temperatures, the building automatically opens the windows and cools the internal slab to keep the building cool through the next day. On summer days, when appropriate, the occupants of the building may open the windows to cross-ventilate this building. Windows on the north sides are operable, and they are also appropriately sized to minimize heat loss and also to help achieve appropriate illumination and cross-ventilation. Again, an excellent example for a cold climate. Let me now talk about hot, dry climates. And hot, dry climates typically occur between the latitudes of 10 and 40 degrees north or south of the equator. They're characterized by limited precipitation, clear skies with intense solar radiation year-round, and large temperature variations between the daytime and the nighttime. A form of cooling is needed, as we mentioned earlier, when the temperature rises above the temperate climate zone. In warm, dry climates, we have the options of nighttime ventilation when the temperatures at night go below the comfort zone, or we can also use evaporative cooling as a means to provide thermal comfort. A form of cooling, as we mentioned, will be needed in this type of climate, but the biggest imperative during the summer is to reduce heat gains through windows and roof surfaces. The use of external shading for windows, the provision of vegetation, outdoor shading, as well as water features may help create microclimates that are conducive to outdoor comfort and become some of the most important strategies that one can use in this type of environment. I want to highlight that in this type of climate, the urban form also plays an important part in the cooling strategies process. In hot, dry cities and towns developed prior to the 20th century, urban form was uniquely developed to maximize shade of the walls and windows, as well as those public outdoor spaces. This is an aerial photograph of Grazalema in Andalusia, Spain. And here we're going to see a couple of images, one of the main plaza and also a narrow street adjacent to it. And we can see in these photographs that in the main plaza, those windows that are exposed to more open spaces have overhangs, as well as other forms of shading, blinds, etc. We also provide additional shading through the umbrellas and trees for the public outdoor spaces to be usable and also comfortable. Also notice the light color in the building facades. And on the photograph on the right, you can see a narrow street typical of this kind of climate. The remains cool during the daytime because it's in deep shade, surrounded by heavy mass materials. And we gain illumination, ventilation, and privacy, all through the use of courtyards as a strategy in this type of climate. So here you see the vegetation, oftentimes evaporative cooling also deployed, having shade through the movable toldos and awnings. And of course, we can ventilation and cooling that way. So I would like to show you an example of a really nice building here in the United States, in Springdale, Utah, with Climate Zone 3B. It's the Zion National Park Visit Center. And here are particulars about this building. Among the most important things, the L-shaped building form with larger facades facing the south, a narrow floor plate, high clear story windows for daylighting, and lower windows for view. In terms of heating, the use of trum walls and direct gain for passive solar. And also for cooling, we have downdraft evaporative cooling towers, also called cool towers, for direct evaporation during the summer. Here's a diagram of the building. We can see that the form is elongated along the east-west axis, much like in the cold climate. And a narrow floor plate permits the proper distribution of daylighting and successful ventilation. And in the wintertime, the trum walls on the south side and the high clear story windows provide the space heating. Appropriate shading for these windows is also necessary during swing seasons to prevent overheating. So here you see a photograph during the spring season. I actually just visited the site this spring, and you can see that the trum wall is partially shaded as well as the clear story windows. But during the summertime, when shading is an imperative, the windows are fully in shade to avoid overheating.
Alfredo, we'll need to start wrapping up to move on to Pablo's presentation.
Yes, thank you, Vince. I'm wrapping up just now. So we have the cool towers to provide the necessary cooling and ventilation in this space, and the clear story and south-facing windows are used to exhaust the warmer air. So you can see that we can take hot, dry air, add moisture to it, and cool it, deliver it to the spaces below. This photograph under construction. And the cooling towers, or the cool towers rather, provide a fascinating and exciting experience to visitors and successful ventilation and cooling of the space. And with that, I'd like to hand it over to my colleague, Pablo Roche.
Okay. I'm going to talk about hot and humid climates. And as we saw, we divide the climates in 4 zones. I'm going to talk about the ones that are closer to the equator, low altitudes, low latitudes, and in which we have high humidities and lower differences between the day and night. These are, if we look at the psychrometric chart that Alfredo showed, they're going to be towards the right and towards the top of the comfort zone, which is sort of this area. It's always helpful to understand climates by looking at where the data is in the psychrometric chart. And what we do, hot and humid climate is going to be warmer outside and more humid than the comfort zone. And it's necessary to keep the building from overheating first and then cool it. And we typically will do this with shade, which reduces heat gains, and natural ventilation, which can evacuate the hot air from the interior of the space. An example of a hot and humid climate would be, for example, San Juan, Puerto Rico. And you can see that most of the year, we are, if not all of the year, pretty much we're towards the right and the top of the comfort zone. We can also see that recommended strategies are also, if we look at climate consultant, are natural ventilation and shade. What is the typical response for buildings in hot and humid climate? It's a thin plan in which you are maximizing cross ventilation and you're providing daylight also. And the smallest facade is towards the east and towards the west. Close to the equator, the sun rises close to the east and sets close to the west, and then spends a lot of time overhead. So the roof is really critical, which must be insulated and providing extensive overhangs. And this shade reduces heat gains through the envelope. If we look at the vernacular response in different climates all over the world, in different hot and humid climates all over the world, we're gonna see common traits. Again, we're providing shade, we're providing permeability through the walls for the air to move, and we're providing some protection from the rain. If we look at the early 20th century response from oil companies that went to the tropics or fruit companies, very interesting proposals, very simple in their conception. Again, we're going to go above the ground to protect from critters and also to provide more natural ventilation. We're also providing more shade above us, more shade uh, 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 with these hats around our buildings. Looking at the layout of these buildings is also important, and they're maximizing natural ventilation, air movement between the buildings, and shade also in these outdoor environments. Now, speaking of outdoor environments, we can also make them better. Traditionally, we're providing shade and air movement, but in this project that we developed in the office at CallisonRTKL, we're going a little bit beyond that and also thinking of radiant cooling. Can we connect liquid-filled tubes embedded in the soil of the planting material that we cool with the earth, we cool with evaporation on top of it, and then these tubes cool panels that are cooling by radiation at the occupant level and at the lower level. And we've done several tests with different types of green roofs. This was developed for a project in Jakarta in a hot and humid climate. And again, we're trying to maximize outdoor comfort by understanding the processes that affect thermal comfort, sort of what Alfredo mentioned in the beginning. And when you combine several of these together, we're not only improving comfort below, but we're also reducing the heat island effect. So multiple combinations of these elements reduce the heat island effect. So in a hot and humid climate, when we think about the envelope, we're have to block solar radiation from the sun, block conduction, and maximize ventilation. When we think of these strategies in architectural terms, we're thinking of maximizing shade, maximizing air movement when appropriate, when it's cooler outside and inside. We're using cool reflective surfaces or maybe even vegetated surfaces. We're reducing heat gains through the building fabric, which is typically done with insulation. And we're reducing the heat gains around the building using shade and cool surfaces. So it's all about reducing these heat gains. And then we can maximize air movement, which is going to remove the heat from the interior of the building and also improve thermal comfort by improving this sweat evaporation from our skin. Shade, there's rules of thumb for shade, but I always think that it's important to understand, develop some sort of workflow and understand climate. So do a climate analysis first. Of course, if it's always hot, we're always gonna need shade, but there is some need for heating during the winter, or there's some sort of heating requirement, then we have to understand that we don't need shade all year. So we have to define these periods we have to look at opportunities. Let me show this here a second. So we got to look, we can do a solar study in which we can find critical facades. We can use Climate Consultant, another tool, to find the required vertical and horizontal shadow angles. And then we test these. Well, we develop a system that we can test for daylight, for glare, for solar gains, and for energy. If the shade system works appropriately, we go on with the project. If not, we go back and we develop another proposal based on these rules. So again, it's really about understanding climate and developing a response that is architecturally working with the building. An example is, this is students at Cal Poly Pomona School of Architecture at the Lao Center working together, developing a proposal for Barranquitas in Venezuela. Uh, it's really about a roof that is floating above you and then air movement down below. We can also use this in, we're not limited to small buildings, right? We can take these concepts to other types of buildings, to high buildings. So in this office building in Shenzhen, we're looking to open the, it's for a competition. We opened to the interior to maximize air movement and maximizing daylight. Again, we test these ideas with building simulation, very important to test ideas with software to validate the ideas. We're looking at exterior solutions. Again, through this courtyard, we're maximizing airflow and maximizing daylight to the interior of the office spaces. And then we have a building that is responsive to a hot and humid climate. Airport terminal and Terminal 2 in Guadalajara. This is also, it's a hot climate. And when we look at conditions in the psychrometric chart, we're not a psychrometric chart, sorry, in temperature, we see that we need shade during all year, and we have a higher solar radiation period from March to July. Again, it's sort of looking at how we control these heat flows, right? How we provide shade, how we block conduction, how we increase long wave radiation through cool roofs, how we have maximize daylight and reduce glare. So just to show you a little bit of the studies that we do. So this is a west-facing facade, right? And which we have to really control the heat gain and the glare. So what we do is that we select a portion of that facade. We don't have to study the whole facade. And then we architecturally, the design team wanted to have something expressive, which is an overhang, which is also reducing. If we look at the heat gain from about 800 kilowatt hours per square meter to about half of that, about 400 kilowatt hours per square meter. Then we added frit. When we study glare, we're looking, this glare study is showing you, this is a person sitting in the waiting area, looking outside towards the west, looking at his plane to see if it arrived or not. And then if we have no shading, we have um, uh, quite significant glare. When we add the overhang, we're reducing the glare. And if we add some frit on the glass, we're almost completely reducing the glare effects for a couple of hours in the late afternoon. If we look at, we did an extensive study of the envelopes just to show you how this works. You know, we studied that period that I showed in the beginning, and we found facades that might have more of an issue, and then we do an architectural response to that facade, right? So we still maintain transparency wherever possible, but we add a little bit more shade in those areas that are more critical. And then we can provide some shade, we can provide some daylight, we can provide views, and still have that control of the heat gain through the envelope. If we go to a temperate climate, conditions are towards close to the comfort zone. And it's really interesting because it's in the summer, it's a little bit warmer than comfort and a little bit cooler in the winter than comfort. So what we need to do is to keep the building from overheating with shade in the summer and cool it with natural ventilation. And in the winter, some sort of passive heating will help. An example is Los Angeles, California. You can see the comfort zone, and you can see that we're pretty close to the comfort zone all year, and some passive heating and natural ventilation is going to help. If we look at the examples, the building response, I would really emphasize sort of this equatorial facing orientation in which we have an overhang. And so we can provide some summer protection and some winter solar gains. And ventilation, it will be helpful when it's cooler outside than inside. We look at the responses. One of my favorite is, Rudolf Schindler, 1921. Really, he started with this whole movement of sort of connecting the indoors and the outdoors, almost very thin walls, work very well in the summer, but not as well in the winter. But again, these are operable. Lots of examples in California, in Southern California, especially. This is the VDL Research House owned by Cal Poly Pomona, built in 1932, and then burnt down, rebuilt in 1964. But again, it's natural ventilation, it's shade, it's daylight, a courtyard. Again, sort of understand these climate forces and a little bit of evaporative cooling. I've had reviews here, and it's really nice to sort of feel how the day changes as you're in the space. You can have, it's naturally ventilated. It might be a little bit cool during the morning, then a little bit warmer, but you're feeling these forces, this sort of change, this haptic changes during the day, which is actually quite pleasant. And then when we think about the heat flows, is really blocking the summer sun and providing some winter heating. So it's very similar to, so there's some protection in the summer and then some allowing of the heat in the winter. An example, I'm just going to show you quickly a couple of examples. One of them is in Tenerife in Spain, is really a project that we developed in which we looked at wind coming from the north east to orient a part of the building, and then solar geometry to orient the other part of the building. And then in the intersection of these two, what you see here is a wind scoop that is providing airflow and natural ventilation to the building. So we have
No, John, I still will need to respond to questions.
So we have ventilation during the summer.
We still have about 15 minutes.
So we still have ventilation during the summer, and then we're blocking the heat during the summer also, and providing some heat gains in the winter. If we see a section of the project, we're looking at, it's all about having the air move through the space, right? And there's even in the upper part of the living room, there's the air, we're inside the wind scoop. The air passes from above us through the living space down to the first floor. Sort of, we're really connected to the forces of nature, to the wind and the sun. The south-facing facade, we don't have a large overhang, but we have operable elements that that slide and provide shade. And this has been monitored by ITER, Instituto Tecnológico de Energías Renovables, and it's really interesting to see the conditions outside are very close to comfort, but the conditions inside are also, this is inside, this is outside, are very close to comfort also. No mechanical heating, no mechanical cooling, and it's just cooled and heated by the forces of nature. So we can see that it's really understanding these principles that can have you operate a building appropriately, opening and closing as required. And this is the last case study. Just quickly, I wanted to show you how using also multiple tools, we can also improve performance in a building. And this is working with our London office. It's a project in Milan, north in Italy. And again, we start with sustainable design, really sort of understanding the climate. We're looking at design ideas shared between sustainability and the design team. And then we have a computational design team also testing these ideas and generating different forms that are tested with rules generated by the sustainability team. So this, and then at the end, there's a validation and testing of these options. So again, we're looking at climate, generating ideas, sketching together, looking at a form that is responsive to the sun and the wind, testing different angles and different tilts and different orientations, finding in a north-south section, which is the critical one in the summer and the critical one in the winter. In the winter, we want to maximize radiation. In the summer, we want to block it. This is going to show us quantitatively with a solar study, and then translating that to a geometry that is tested also with different types of louvers and to find the best option, to find the best fit. And then tested for energy and for daylight. So the idea is the same design team in London generated this project in Australia. The idea is that we generate an interior space that is responsive to the outside, but it also enriches the experience on the interior. So just finally, so what should we do when we're talking about carbon neutrality in buildings? I think Alfredo and I would say that we should always respond to climate first. Climate responsive buildings cool and heat without generating CO2. They reduce the building's carbon footprint and are exciting because they offer design opportunities. Thank you.
Thank you so much, Pablo and Alfredo. Really amazing presentation, and wonderful to see some of the results of this climate design. We have one question that came in. We've got about 2 minutes left in the session, and then we'll have to close it. So I think we'll have enough time to answer this. Pablo, I think this might be specifically for you, but I'm sure Alfredo, you could talk about this as well. It says, do you have energy consultants within the architectural design firm's office in-house? Or do you run simulations through collaborations with your engineering teams? What engineering modeling tools were used for the design facade analysis through the example in the hot humid case study you've shown for building response? Thank you very much. Gorgeous and helpful presentation.
Yes, absolutely. We do, I always say we do conceptual energy modeling in-house. So we do, all the simulations that you've seen here were done in-house. So we do that as part of our team. We work very closely with designers to, I always say, to generate ideas and to test them. So we really try to do all of that in-house. Everything that has to do with the envelope and the architecture, with testing different shade options, different daylight studies. We've used different types of programs. For example, I think the solar study that that he's asking we did with Diva, which is a program. It's a plugin that works with Rhino.
Great, thank you. We've got about 1 minute left. Paula, Fredo, I don't know if you want to talk about some of the design simulation tools that you've used in teaching and you see in practice.
Thank you, Vince. I think Pablo did a fantastic job showing some of the tools. You know, obviously Climate Consultant is a really good tool that I strongly recommend. And then the strategies may be simulated in a number of ways, either from, you know, simple rule of thumb calculations all the way to full simulation using, you know, Energy Plus or other software. So my recommendation is use the tools that seem appropriate to the scale of the project and the stage of the design process in which you are. But certainly the first and most important step starts with the simple sketches that begin to set the project in the right direction by looking at a good climate analysis. Great.
Well, thank you both. That is all the time we have for today. If you have additional questions, feel free to email them to CarbonPositive website, an email address, which you should have from your agenda. And also wanted to note that, again, thank you to Pablo and Alfredo for a wonderful presentation. We will have a recording of this presentation available on the CarbonPositive website as well. So that concludes this session. For the next session, please go back to the carbon-positive.org website and go to the agenda page and select on the next session's links. So thank you very much again, Pablo and Alfredo. Really appreciate you getting up early and presenting this to the Europe, Middle East, and Africa region. Thank you.
Thank you very much.
Thank you. Bye. Thank you so much.